In this lesson, we will brief about AVL trees or height balanced trees. AVL tree is the first balanced binary search tree, which is named after its discoverers Adelson, Velsky and Landis. The AVL tree is a balanced search tree that has an additional balance condition. The balance condition must be easy to maintain and ensures that the depth of the tree is order of log n, where n is the number of nodes. Already we know that height of a tree is the length of the longest path from the root to a leaf node. A binary search tree T is a height balanced K tree or HBK tree if each node in the tree has the HBK property. A node has the HBK property if the height of the left and right subtrees of the node differ in height by at most k. HB1 tree is called as AVL tree. That is, the left subtree minus right subtree height will be at most 1. In a nutshell, an AVL tree is a binary search tree that is height balanced, meaning that it has the following two properties. The subtree of every node must differ in height by at most 1. And every subtree is an AVL tree. For example, consider the following figure. We have a node with left subtree height h minus 1 and right subtree height h minus 2. The height of the node is h. The difference between these left and right subtrees is 1. Like this, every node has to have that property. Then only it can be called as the AVL tree. At any point, the left subtree or right and right subtree difference should be at most 1. For example, the following trees. The first figure, if you verify at each node, the left subtree minus right subtree height is not more than 1. Thus, it is a balanced tree. For example, at node 5, if we calculate left subtree height 2, right subtree height 1, 2 minus 1 is 1. So, if we calculate at 4, 7, 3, we may find that the left subtree minus right subtree values are not more than 1. Thus, the tree is balanced tree, rather AVL tree. Whereas 2, it is not. For example, at node 10, if you verify the left subtree height is 3, right subtree height is 1, thus 3 minus 1, it is 2, which means that that tree is not a AVL tree. For example, the following figure, if you verify, it is also not a AVL tree. At nodes 8, 4, 3, the left subtree minus right subtree height, it is not satisfying the requirement of 1. The following tree is a height balanced tree, AVL tree. You can verify the balance values by the side of the nodes. Also, take the following two figures. The figure left hand side is a AVL tree, whereas the right hand side is not a AVL tree. Property, left subtree minus right subtree property is not satisfying at root node 7 for the right subtree, right hand side tree. If you verify, this figure is also a AVL tree. This is not an AVL tree. At root node, the property is not getting satisfied. This is another example for AVL tree. This tree cannot be called as AVL tree. Just to explain what is the difference between binary search tree and AVL tree, consider some airport names and we try to maintain them in the binary search tree fashion and also AVL tree fashion. This is the binary search tree for the airport names. This is the AVL tree for the same names. We know both binary search tree and AVL trees are for searching purpose only. While searching, we traverse from root node and we go on move downwards, either left or right based upon the value available in the nodes and also based on the key what we are trying to search for. The successful search, the height, how many places we have to carry out the search. Worst case, that is same as the height of the tree. Best case, at root node itself we may get satisfying our requirement. If we verify both the graphs, that is binary search tree of these airport names and also AVL tree representation of the airport names, if we verify average number of comparisons, which is sum of all path lengths plus 1 divided by number of nodes, that indicate the average number of comparisons. If that is calculated for the binary search tree, it becomes 39 by 11. 11 means there is the total 11 airport names are there, that is 3.55. For the AVL tree, it is 33 by 11, that is 3.0, which means that average number of comparisons required for binary search tree, AVL tree becomes less because of the better organization of the names. Like this, AVL search tree gives better performance than binary search tree. That is the reason why we are supposed to know about it. In a nutshell, the following comparison will help us to know more about the AVL tree in comparison with the binary search tree. In a binary search tree, insertion, deletion, search requires order of n, worst case. Whereas in the case of AVL tree, all of them worst case requirement is order of log n. And we already know that order of log n is much smaller than order of n. Thus, AVL tree's performance will be good even in the worst case also. However, the AVL tree creation adds complexity, that is extra complexity. We know that AVL tree we require to maintain the property, that is the left subtree height minus right subtree height should not be more than 1 always. Whenever we carry out the insertions, deletions, this property has to be maintained. This requires little more efforts. This is the little demanding one in the AVL trees compared to binary search trees. For example, in the following figure, if we insert a node to the right hand side subtree of the root node, then we may find that root node will be having unbalance. That is, left subtree height minus right subtree height becomes more than 1. In order to maintain the balance, we may have to do some operations, which we normally call as rotations. We will be discussing in the coming slides about it. So this type of unbalance will come into the tree. we have to rebalance such a way that the property of left subtree minus right subtree should not be more than 1, has to be satisfied always. Consider the following simple examples also. So if we, in the first figure, if we add 1, that is insert 1 into the binary search tree, AVL tree, which is already AVL, after insertion, it will be losing the AVL property. So we have to bring it to such a way that the property will be maintained. Similarly, the second figure, if you see, before and after deleting 7, before deletion, it is having AVL property. After deletion, the tree is losing AVL property. So thus, we have to bring it to, again, AVL form. That requires some balancing. Balance factor of a node is defined as left subtree height minus right subtree height. Always we have to maintain at every node the balance factor should be in between -1 to 1. So this property has to be maintained to call it as a AVL tree. Whenever we insert, whenever we remove a node from the tree, that property has to be maintained. So this is the requirement of the AVL tree. Normally this is little time consuming one compared to binary search tree operations of insertions and deletions. However, remember, in the binary search tree, while creating the binary search trees, if I give numbers, or the numbers whatever we enter all in the ascending order, then we understood that we will be getting a skewed tree. The search complexity becomes order of n. Whereas, in this case, as we are trying to do, rotations or adjustments whenever we insert a node, and if you find that the tree is losing the property, we will be doing some adjustments such a way that tree again comes to the AVL fashion. Thus, never the tree becomes skewed tree, and always the complexity will not be more than order of log n, where n is the number of samples. That is the advantage of AVL tree compared to binary search tree. This slide shows balance values for all the nodes of the graph, a tree given in the slide. If you verify, all the balance values are in between -1 to 1. Thus, it is a AVL tree. This tree is not a AVL tree. The root node is having balance value of 2. Thus, it is not a valid AVL tree. Whenever we insert or delete a node from a AVL tree, there is a danger of losing AVL property. At that junction, we apply some operations known as rotations or shifting operations, so as to maintain the balance property of the AVL tree. Evidently, there are two types of rotations known as single rotation and double rotations. They are required to be performed whenever we miss balance at any given node. Consider the following tree. Two nodes, the root node is n and its left children is c. C is having subtrees of height h minus 1 and the root node n is having a tree of h minus 1. However, if we consider the tree T1, T2, T3, they are the subtrees. So the T1 minus T2 heights, it is 0. So at C, the balance value is 0. However, at N, the balance value is H minus 1. That is 1. That way, the tree is a AVL tree. Now, let us assume that we have inserted a node to the left hand side of the node C. Thus, the left hand subtree height of the C becomes H plus 1. Right hand is H, and whereas the root node right hand is H minus 1. If you calculate the heights, or rather say BF value, balancing factor value at C, that is H plus 1 minus H, that becomes 1, that is balanced. Whereas at node N, that is root node, H plus 1 minus H minus 1, that becomes 2. That is at root node, we will be having unbalance. To bring it to balanced situation, we have to rotate the tree. Balance is, rather I say, height is more which side? That is left hand side. To bring it to balanced balanced thing, we have to move the tree to right direction. We assume that at root node N, there is a unbalance. That is, the balance value is more than 1, that is 2. So we have to apply rotation at N. And also, we verify that the node is added to the left hand side of the N, and also it has added to the left hand side of its parent. So to bring it to balanced, we have to apply right rotation. So the function is given in the slide. We consider that C now will come into the place of N. By chance, if N is some child of some other node, so into that place C will go, and also C's right subtree becomes N's left subtree, and we'll make N as the right to C. Mind it that after rotation, the in-order sequence also has to be preserved. That is most important thing. We are all doing this one for efficient searching operations. Thus, AVL tree is a binary search. It is a search tree only, which means that property has to be satisfied. What is that property? All the nodes whose values are more than current node should be right hand side, and less than should be left hand side. That property has to be maintained. So to achieve that one, we know that C's, those values which are more than C, node C value will be right hand side. So they have to be now left hand side of N. What is the relationship between key values in C and N? So C value will be less than N. However, those values which are greater than C are in the right hand side of C originally. So those things will make it as left children for N. That is to maintain the in-order sequence. For example, consider that we have inserted 60 first, then 50, then 20. When 20 is inserted, the tree becomes unbalanced. And also remember, if you traverse this tree before balancing in order fashion, what are you going to get? 20, 50, 60. Now let us assume that the rotation took place. The balanced tree is as shown in the figure D. If you traverse this one in order fashion, still you are going to get the same in order sequence, that is 20, 50, 60. So that is, we have to maintain the in order sequence. That is another important aspect in the rotations. Similarly, consider this situation. Here we are having two nodes N and C. N is having a left subtree of height h minus 1, and the node C is having left subtree and right subtree T2, T3 of height h minus 1. Both N and C, as of now, they are balanced. Now let us assume that a new node is added to the tree, that also it is added to the subtree T3. Thus the subtree T3 height becomes increases. Thus the node C is balanced, but however node N becomes unbalanced. That is, its right hand side subtree height will be more than left hand side subtree. As it is unbalanced towards right side, so we require to bring it to normal fashion. Thus we require left rotation to be applied. So that is tree, we have to move to the left side. Now the rotate left function will be assumed to be called. The rotation has to be done about N. Remember that if the tree, whatever we have shown, if it is rooted at N, if it is support of another tree, into that portion, so for example N, previously it was a left child of some other tree, some other node of the some other tree, then into that place C will come. That is the first important aspect. That is N's place C will occupy, and then N becomes C's left child. Similarly, C's left child's left subtree becomes N's right subtree. Thus, the in-order sequence will be preserved. Remember, if you verify the in-order sequence, after processing N, we will come to C, and then C will not be processed. C's left hand side 4 nodes will be processed. So that order has to be preserved. So after rotation also, if we verify, after processing N, what are we going to process? We are going to process the T2, that is the tree. Then only will come to C. That in-order sequence has to be maintained after the rotations. That is the most important aspect. I am sure that users understood this concept. Let's consider the tree A, which is balanced. Now when we add 90, tree got unbalanced. The nodes, that is 60 and 50, they got unbalanced. Their balance values are -2s. Now by adding 90, which is the youngest ancestor of 90 got unbalanced, that is 60. So that node we have to say select. About that we have to rotate. Remember, we are talking repeatedly. So now what is the subtree portion which got unbalanced? That is 60, 80, 90. So now currently 60 is right child of 50. So now while applying the rotations, that is left rotation. So we consider n as 60 and c as 80. Then the rotation we have to apply. And remember, that is n's place c will come. That is 80 now becomes the left subtree, right subtree of the 50. And for that 80, the n that becomes a left subtree. Thus 60 goes here. Now if you verify, after balancing, the in-order sequence is preserved and also the tree is balanced. Just for the sake of clarification, we are adding some more slides. Consider the tree as shown in the slide. Node A has -1 balance value, indicating that right hand side is more. Node B is balanced, that is left subtree height is h, right subtree height is h. So the balance value is 0. When we insert a node to the tree, that also to the right hand side of the node B, its height becomes h plus 1. Thus balance value of B becomes -1, whereas balance value of A becomes -2. You can verify in the slides. If we apply left rotation, the tree becomes as shown above. The nodes A, B balance values become zeros, and also in-order sequence will be preserved. Now consider a situation. The tree is as shown in the slide, that is nodes n, c, g are available. The left hand side subtree height of n is h minus 1 and right hand side tree height of c is h minus 1. Left hand side also h minus 1. Thus c balance value is 0. N balance value is -1. Similarly for node G, the left hand side, right hand side subtrees or heights are same, h minus 2. Thus balance value is 0. Now consider a new node is added to the subtree T3. Thus the T3 subtree height becomes increased by 1. Thus balance value G becomes -1, acceptable. Similarly, balance value of C becomes +1. That is, the left hand side is 1 more than the right hand side. However, balance value of N becomes -2. That is, N becomes -2 means N becomes unbalanced. So, however, the situation demands 2 rotations. With one single rotation, we cannot achieve the balance. First, we rotate about C, and then we'll rotate about N. We rotate the subtree rooted at C towards right direction. The rotation is at about C only. Thus, when you rotate about C, if you verify the previous slides, C's place G will be taking, and C becomes the right child of the G, and G's left children becomes G's right child becomes G's left child. This is to maintain the in-order precedence. However, if you verify, the tree is yet unbalanced. Now we apply left rotation about n. Thus n's place g will come. N's left children becomes g's left children becomes n's right children. Thus the tree will be as shown in the slide. If you verify the balance values now, n balance value is 1, c balance value is 0, and g balance value is 0. In this example also we require double rotation. Here first we require left and then followed by right rotation is required. Algorithm rotate left right is produced by first we have to identify the nodes C and N having that property what we have explained previously. About C first you have to apply rotate left, and then about N we have to apply right rotation such that the resulting tree will be in a balanced fashion. Consider the tree in the figure A. We may check that the tree is having balance. When we insert node 35, the tree becomes unbalanced. Left rotation about 40 gives the following figure. After right rotation, the tree becomes as shown in the slide, which is a balanced tree. Similarly, rotate right left requires first right rotation, then followed by left rotation. You can verify the slide. if we add a node and if we find out the path of the node, if you find all the nodes along that path are having balance value is 0, by adding this new node, we need not require any rotations. Thus, as adding this node will not disturb the balance values along the path.